Okay, let's start off basic with elements. So element is going to be a pure substance. So I'm going to come over here and put a text box in right about here. Okay, so elements, pure substance in which there is only one type of particle. Okay, so with elements, you only have one thing, one color, okay? One substance, one pattern. That's it. That's all you've got on an element. Now, you can have elements that are what we call monatomic and diatomic and polyatomic, whatever. But there's only going to be one type of particle in all of these. There's 118 elements on the periodic table. You will be able to recognize these because they have symbols. So the 118 elements on the periodic table have chemical symbols. So like things like hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Sodium is next. Magnesium. Okay, I could keep going down the list. But here's what you should notice. They all have capital letters, okay, and then maybe a lowercase one. But if you see a capital letter, it's telling you that that substance is an element, okay? So here's where the particle diagram comes in. If I want to make this box over here an element, I'm going to put these guys in, and I notice that every one of these particles in here, and try to match them up. I'm going to actually copy and paste that, make this go a little bit faster, are all the exact same thing. Okay, so when I look at this particle diagram picture, I'm like, hey, this is a pure substance because everything in this picture is exactly the same. Okay, now two things can be pure substances, elements and compounds. So now, how do I know that this is element? There's only one of these types of particles. There's not two things bonded together. There's only one. Now, this picture is going to show us a couple things. Okay, so I'm going to insert another text box right over here. And I'm going to tell us that this picture is going to show us a solid because they're closely packed together. It's a monatomic element because mono means one. So there's only one type of particle here. They're just really close together and vibrating in these fixed positions. So element is the smallest thing we can have. You cannot break down elements. Okay? So if you are given an element, you can't get anything smaller. You're not going to break it down. Now, there are parts that make up elements, yes, but you then no longer are talking about that whole particle. Okay? So elements cannot be broken down by any means. No physical, chemical, nothing. Okay? Okay. So now we're going to look at our little sample over here, and we notice once again that this is an element because everything in here is a pure substance. All of the particles are exactly the same. Okay, so it's a pure substance. But now when you look at this element, you notice that there's two of these elements, and you can see that they're attached together. So they're the same color, which makes them an element, but they're just bonded together. So this is what we call diatomic element because di means two. Like you throw two dice when you play a game with dice. Di means two. So diatomic. Now this picture that I just drew, instead of being a solid, is actually a gas because you can see that the particles are spread out. They're taking up all their available space. They have an indefinite shape and an indefinite volume. So this is a diatomic element. Okay, so if you look over here to the left of the things that you've been given, I want you to kind of take a moment and think of all these colors that you've been given, which would be elements, and of those elements, which would be monatomic and which would be diatomic. All right, I gave you a second. Let's see how you did. If you said that the white would be a monatomic element and the yellow would be a monatomic element, you're doing good. If you said the red would be a diatomic element and the yellow would be a diatomic element, then you've got it. And you've got element, your first pure substance. All right, next. The next thing that we're going to talk about is a compound. A compound is a pure substance. Okay. However, the compound is two or more elements chemically bonded. Okay, they're chemically bonded and combined. Now, specific ratios. Okay, so you can't just throw them together however you want. Like H2O is always H2O. H2O2 is always H2O2. CO2, CO2. They're very specific on how they come together, okay? Specific ratios, and the elements gain new properties when combined to form a compound. They are no longer what they once were. They now have new properties to them to form that bond because they've been chemically bonded. And if it's chemically bonded, it went through a chemical change. Okay, still a pure substance, and I'm going to show you why. So I'm going to bring this over here. Bring this over here. Oops. Hold on. There we go. Sorry, I messed up and went too far. Put that bad boy over there. Put this guy over here. Maybe we'll go there like that. A little bit like this. Give a little bit of space. I'm going to move him just a tad. Yeah, that works pretty good. And maybe let's go another one over here and move this guy around just a tad bit. Okay. So here's what I want you to take a look. This is a pure substance because as you look at it, you can see that every particle in here is exactly the same. It just so happens, though, that these particles are made of two colors, two elements. So you've passed the element stage. Element was one thing. You are now at a compound because, like, think compound sentences. It's two parts. Compounds are two parts at least, okay? So if I take a look at these elements, it's made of a green element and a red element. Okay, no, we don't have green and red elements, but it's made of a green atom, red atom. So these are two or more elements that have been chemically bonded, and we can see that by how they're attached. Okay, so this is a pure substance because if we look here, every single one of the particles is exactly the same. They just happen to be a compound. So compounds are pure substances. Now, the specific ratio, look at each one of these. It's GR2. One green, two reds. So GR2, 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 GR2. Now, there is no green element and no red element. I'm just giving you how those chemical formulas would look. So now I'm going to come over here. I'm going to tell you what we got going on. We've got a compound that is currently in a liquid form because the particles are able to slide around. You can tell that some of them are moving up around each other. They can slide and glide. They have a definite volume. Like I know exactly how many particles are here. I can see like what the volume is going to look like. They do not have a definite shape, and that's why liquids can take their shapes of their containers. So what I would like you to ask yourself now is looking over here to the left, which of the items would be classified as compounds? Go ahead and go. Let's check and see how you did. So over here, if you said the blue, so BW2 was a compound, then you would be right because it is two or more elements chemically combined, and we see the very specific ratio. Next, if you said the BR was a compound, you would also be correct. We should know that the GR2 was a compound because we looked at it already. We've got WEY3 is a compound, and GY would be a compound. Okay? So any of them that had two or more substances combined were compounds. All right, let's take a look and see what we've got going on here. So this slide is asking us to make a mixture of diatomic elements and compounds. So I'm going to look, and my red is a diatomic element, and so is my yellow. Okay, so remember, elements, one type of particle, just red, just yellow. Di means two, so there's two of them. So mixtures here are two or more substances physically combined. Physically combined. So there's no chemical bond. They're not attached to each other. They're just physically combined. They're just all mixed together. No specific ratios. Okay. Properties remain unchanged. So what that means is that just because, I'm going to move this up a little bit here, just because you've now put them together, they are still what they once were. We had pizza tonight. We had pepperoni pizza. The pepperoni, if one of my kids doesn't like it, fine, take it off. It does not affect the pizza because we took off the pepperoni. Mixtures do not matter how much cheese, how much pepperoni you have, doesn't matter. It's just all mixed together. Okay. If I don't like something, take it out. Does not affect the overall thing. If I don't like my hydrogen in my water, I got a problem. I can't take out hydrogen from water because water's H2O. You can't take apart the compounds and keep the same properties, but a mixture, you can't. So two or more substances just physically combine. So mixture of diatomic elements. I'm going to grab some of the diatomic reds here and just kind of move them around because make them look a little bit better. Okay. Then I need a compound. So why don't I take this guy and then put him right there and take another one, put him down here, kind of spin this one a little bit. Oops, totally just messed that up. Hang on. Sorry. That's what I get messing with this on my computer. And maybe let's just throw another one of those little guys up there and let's change him, make him kind of go like that. Sure, that looks good. Okay, move this guy down here. All right, let's take a look. You have a mixture. How do I know? Because these two things, the red and the green and yellow, are not, okay, bonded right here. So this is separate from this, and this is separate from this, and this is separate from this. So you do not have anything bonded here between the two substances. You just have a mixture. Okay, so now we're going to look at what we did. Mixture of diatomic elements. Okay, diatomic element, diatomic element, diatomic element. Compound, compound, compound. What form is this in? If I come right here, this is a gas. Okay, so a gas mixture of diatomic. How do I know it's a gas? It's filling up its container. They're spread out. They're not strongly attracted to each other. There isn't a definite shape. Gases don't have definite volumes because if I were to leave this open over here, okay, then you would see some of them leave. They can leave, they can come in, you can constantly change that. So this is a mixture. I look at this mixture, I don't see any part of it that is jumping out at me saying, hey, there's definitely a big difference here. So this is a homogeneous, whoops, hold on, homogeneous mixture because the prefix homo means same. Okay, so the prefix homo means same. So maybe I'll put that right here. So homo, if I could type, means same. So if you are ever given anything that in science, like Homo sapien, you're homogeneous, homo thermic, anything like that, it's the same. Same, same, same. Okay. So this looks the same throughout. What I mean by that is that you don't see any part of this mixture that's completely different. You see a couple elements, you see a compound, you see an element, you see a compound, compound, element. They're just nice and evenly distributed throughout. This is homogeneous, okay? You got to get through your head that a homogeneous mixture does not mean every particle in here is going to be the same. That was pure substances. Mixtures are not pure substances because they are mixed. They are a mix of multiple things, not a pure substance. Pure means pure. Mix means mixed. Not the same thing. Okay, I'm going to go on to our next slide here. So our next slide was asking us for a mixture of two compounds. So I took two compounds. I look at this. I see that this is a mixture. Currently, it's in a gaseous state. Okay. Now, what if I did this, moved this down, moved this down. I'm going to copy those, paste another one right in here. Okay. Paste another one down in here like this. Okay. And another one. Kind of move him right here. And then I'm going to move these guys kind of up like this. Whoops. And let's do another one of those. Copy, paste. Okay, let's do another one. I'm going to do it right here. Okay. Let's take a look at this picture now. Think to yourself, what are you seeing? Okay. Hopefully you had a chance to think. I got a mixture of two compounds. One of these compounds is a gas. So let's focus in right here. These compounds are gases. They're spread out. These compounds are liquids. They're close together. They don't have that repeating pattern. You can tell that they're kind of trying to slide and glide past each other. So you are a mixture of gas and liquid. Okay, so maybe like pop. Pop has gas in it. You got your liquid. This is when you open your container and your gas starts leaving it. You're left with the pop behind. Now, if you do it well, you don't get the liquid to fly out of your can. Okay. You should, however, when you open the can, hear that little that's because some of the gas is leaving. Okay. When you look at this picture right here, okay, this picture right here, you can tell that there's a difference between the two. Now, I probably shouldn't use pop as an example because looking at it, you typically don't see the pop leaving or the gas leaving unless you've shaken it up and like caused it to all take off the top. So maybe this is the oil and water bottle in my classroom. Okay. You see the water down below. You got some oil on top. Now, oil wouldn't be a gas, but you know what I'm saying here. Okay. This is now a heterogeneous mixture. So this is a heterogeneous mixture of two compounds. Okay, so this compound keeps its properties, this compound keeps its properties, and one of these is a gas and one is a liquid. So I want to point out to you guys, notice that we just keep building on it. We know if it's an element, compound, or mixture. We then know, is it solid, liquid, gas? Notice we haven't run across plasma because plasma is a charged particle. We then are able to tell you, what's happening between these things. Are they mixing? Are they going to be chemically combining? You're able just to build another layer on top of it. All right, let's check you. What do you think this is? If you said compound gas, you are right. All right, next question. What do you think this is? If you said a diatomic element in most likely probably gaseous form, then you would be right. Maybe liquid, but I would say more gaseous because from the view we're getting, they're spreading out. It's an element, it's a pure substance, and it's a diatomic. All right, what do you think it is? If you said compound, pure substance, liquid form, now this one I can safely say it's a liquid because you can see how close they are together, you would be right. What do you think it is? If you said a heterogeneous mixture of monatomic elements in a most likely kind of liquidish form and gaseous form, you would be correct. Okay. Biggest thing on this one would be it's a heterogeneous mixture because you see a different section to this. You see one section that's here, you see another section's here. You would definitely notice looking at this that there's a different section to that substance. And our last one here, because I went longer than I wanted with this video, what do you think it is? If you answered that this is a homogeneous mixture of monatomic elements in a gaseous state, you would be correct. Okay. By the way, these fireworks are compounds that we burn, just so you know. Okay. But they're mixed with gunpowder, which then makes them a heterogeneous mixture if you've ever actually seen a firework. Sorry, had to add that to the mix. Kid it, mix. Okay, sorry. It's late. I'm still telling bad jokes. It is what it is. Okay. Hopefully this helped. Like I said, it was a little bit longer than I planned, but you can use it as much or as little as you wanted, and go from there. If you need something else from me, please ask.